on my interview. Today I'm gonna make a big announcement on my latest creation, introducing FearMax, a digital and also physical ecosystem that can be easily deployed at your own home. I have bring out the latest model of FearMax itself. So this is truly something one of a kind and absolutely significant. It can march around swiftly with its 4 wheels. It can process data within milliseconds. It can also travel in a maze effortlessly and also recognize the images with very high accuracy. And let alone, we also have a very user-friendly UI in our phone tablet for the controlling of this robot.
What do you mean by your creation? This is a team effort, okay?
Alright, my bad for taking up all the credits. Then maybe y'all want to introduce what you did for this project one by one?
Alongside the ultrasonic sensor in front of the STM, there are also 2 infrared sensors facing the left and right of the robot. This is to ensure that the robot has enough space to perform a left or right turn. And when it does, the gyroscope on the STM helps the robot perform accurate 90-degree turns. The robot can also see what's ahead thanks to the big camera mounted facing the front of the robot. With these sensors, the robot is now aware of its surrounding and can move around intelligently.
The Raspberry Pi is in charge of the communication between the Android tablet, the STM32, and the laptop that hosts the image recognition and pathfinding API. We achieve this by using Bluetooth sockets to connect to the tablet, PySerial to establish a serial link with the STM32, and Python Flask to house the APIs that we can call from the Raspberry Pi. We also used a multiprocessing library to ensure that our Raspberry Pi can send and receive messages from the different components concurrently.
Don't worry, we're here to give you guidance. Our pathfinding algorithm firstly receives a dictionary of the robot and obstacle positions and facing from the Android app. It sorts the obstacles to be visited in an ascending order in a tuple, using the distance from the car start position to each obstacle. A simple A-star search is then implemented based on the 20 by 20 virtual grid in the arena. For each obstacle previously sorted out, the heuristic is calculated using the distance from each grid to that obstacle, hence output the desired path. For obstacle avoidance, each obstacle is considered as a 3 by 3 grid that the car cannot enter. Finally, the path is returned to STM as a dictionary of commands for car movement.
Talking about me, let me show you the Android app. The Android app is responsible for providing an easy-to-use user interface for controlling the robot. The Bluetooth interface allows the user to discover, pair, and connect to nearby Bluetooth devices. The command and control section allows for any message or command to be exchanged between the app and the robot. Setting up the arena is as easy as tapping the arena and selecting the desired options. Changing the position of the obstacles is achieved by dragging the obstacles to the desired position. It is also equally easy to remove an obstacle. Any change to the position of the obstacle or the robot is transmitted immediately for processing. The robot's position in the arena can be updated when the robot moves, and the images it recognized are shown on the respective obstacles. The app also supports the reset of the arena.
Wait. Don't forget you need to recognize the image in the maze.
For image rec, the first step is to upload all the images that we've taken into RoboFlow, which is a website to label, prepare and host our dataset. Then, we generate the dataset after adding a pre-processing step called AutoOrient, which decreases the training time and increases performance. Next, we train a YOLO V5 model using a Google Colab environment, which utilizes Google's GPUs. After training is complete, a best checkpoint is saved as best.pt, which can be used to run an inference on new images.